The nonlinear Schrödinger equation, or NLSE, is one of the most important equations in modern wave physics. It describes how waves evolve in nonlinear and dispersive media. But what does nonlinear actually mean? In ordinary linear systems, waves travel through a medium without changing its properties. But in nonlinear systems, the wave itself modifies the medium as it propagates. For example, in nonlinear optics, the refractive index changes with light intensity. This means the wave changes the medium, and the modified medium acts back on the wave. This feedback mechanism is what produces fascinating phenomena such as solitons, rogue waves, and supercontinuum generation. And remarkably, the same mathematics appears not only in optics, but also in ocean waves, quantum fluids, and even biological systems. As you can see in the equation on the screen, this is the standard form of the nonlinear Schrödinger equation used in optical fiber physics. The term on the left describes how the wave envelope evolves during propagation. The first term on the right represents dispersion. It causes different frequency components of the pulse to travel at different speeds, which makes the pulse spread out in time. The second term is the nonlinear contribution. It comes from the Kerr effect, where the refractive index depends on light intensity. An important detail is that the variable t here is not absolute time. It is the retarded time frame moving together with the pulse. To understand why the equation is nonlinear, we need to look at how the refractive index behaves in nonlinear optics. As shown on the slide, the refractive index depends on intensity. Since intensity is proportional to the square of the wave amplitude, stronger parts of the pulse experience a different refractive index than weaker parts. This creates a feedback loop. The wave modifies the medium, and the medium modifies the wave. This is the physical origin of nonlinearity in optical fibers. Dispersion can be understood more clearly in frequency space. As shown in the expansion on the slide, different frequency components propagate with different velocities. The parameter beta 2 determines how strongly the pulse spreads during propagation. As a result, even if a pulse starts very short and localized, dispersion causes it to broaden over distance. This effect is unavoidable in most wave systems. Now let's look at the nonlinear effect called safe phase modulation, or SPM. Because the nonlinear phase depends on intensity, the center of the pulse accumulates phase differently from the edges. This changing phase creates new instantaneous frequencies inside the pulse. This phenomenon is known as chirping. So while dispersion spreads the pulse in time, self-phase modulation broadens the pulse spectrum in frequency. To better analyze the equation, physicists often normalize the variables. As shown on the slide, characteristic length scales are introduced. One of them is the dispersion length, and the other is the nonlinear length. Their ratio defines the dimensionless parameter n. This parameter tells us which effect dominates the system. If n is smaller than 1, dispersion dominates. If n is greater than 1, nonlinearity dominates. But the most interesting case happens when n equals 1. That is the soliton condition. To search for stable solutions, we assume a special mathematical form for the wave envelope. After substituting this form into the NLSE and separating the terms, we obtain a nonlinear differential equation for the pulse shape. This equation describes the balance between dispersion and nonlinearity. Interestingly, this nonlinear equation can be interpreted like the motion of a particle inside a potential well. As shown in the slide, the effective potential creates a stable configuration. This stability is the reason why solitons can preserve their shape over very long distances. Unlike ordinary waves, they behave almost like particles. As shown in the equation on the screen, the solution has the shape of a hyperbolic secant function. This pulse maintains its shape because two competing effects exactly cancel each other. Dispersion tries to spread the pulse, while nonlinearity tries to compress it. When the balance is perfect, the pulse becomes a soliton. This is one of the most beautiful examples of self-organization in physics. However, solitons only exist under specific conditions. In optical fibers, they appear in the anomalous dispersion regime, where beta 2 is negative. In real communication systems, losses inside the fiber gradually weaken the pulse. This is why practical soliton communication systems require optical amplifiers to periodically restore the signal. The same nonlinear equation can also describe extreme wave events known as rogue waves. As shown on the slide, the Peregrine soliton predicts that wave intensity can suddenly become dramatically larger than the surrounding background. At the center of the solution, the intensity becomes 9 times larger than the background wave intensity. This explains how unexpectedly large waves can suddenly emerge in the ocean. But where do rogue waves come from? One important mechanism is modulation instability. Tiny fluctuations inside the wave grow exponentially because of nonlinear feedback. Over time, energy becomes concentrated into localized regions, producing extreme wave events. Although the model shown here is idealized, similar mechanisms are believed to contribute to real rogue waves in oceans. The nonlinear Schrödinger equation also appears in quantum physics. In Bose Einstein condensates, it takes the form of the gross Pitaevskii equation. Here, the wave function describes an entire quantum fluid rather than a single particle. At extremely low temperatures, many atoms behave collectively as one macroscopic quantum wave. The nonlinear term in this equation comes directly from interactions between atoms. The scattering length determines whether the interactions are repulsive or attractive. Repulsive interactions help stabilize the condensate, while attractive interactions can lead to collapse or bright soliton formation. So once again, nonlinearity controls the large-scale behavior of the system. When a Bose-Einstein condensate rotates, it cannot rotate continuously like an ordinary fluid. Instead, circulations becomes quantized. As shown in the equation, the phase must return to itself after a complete loop. This creates quantum vortices with nearly zero density at their cores. These vortices are among the clearest manifestations of macroscopic quantum mechanics. One of the most remarkable things about the nonlinear Schrödinger equation is its universality. It appears in optics, hydrodynamics, plasma physics, quantum fluids, and many other nonlinear systems. Different physical systems can behave in mathematically similar ways because the same balance between dispersion and nonlinearity emerges repeatedly in nature. For ultra-short femtosecond pulses, the simple NLSE is no longer sufficient. Additional higher-order effects must be included. These include third-order dispersion, self-steepening, and Raman scattering. Together, these effects distort the pulse shape and shift energy toward longer wavelengths. Accurate modeling of modern ultrafast lasers requires these corrections. When many nonlinear effects act simultaneously, something extraordinary can happen. A narrow laser pulse can evolve into an extremely broad spectrum containing many different colors. This phenomenon is called supercontinuum generation. It is sometimes described as creating white light from a laser. Supercontinuum sources are widely used in spectroscopy, metrology, and biomedical imaging. Some researchers have proposed that energy transport inside biological molecules may also involve soliton-like excitations. According to the Davidov model, energy could travel through protein chains as a stable localized pulse rather than dissipating as heat. However, this idea remains controversial, and there is still no complete scientific consensus about it. The nonlinear Schrödinger equation forms a bridge between mathematics and reality. It connects optical fibers, ocean waves, quantum matter, and possibly even biological systems. Its importance comes from a simple but profound idea. Our universe is fundamentally nonlinear, and in nonlinear systems, small effects can grow, interact, and organize themselves into complex structures. Solitons, rogue waves, and quantum vortices all emerge from this deep interplay between nonlinearity and dispersion. In many ways, the nonlinear Schrödinger equation reveals how order can arise from complexity itself. Thank you so much for watching. I hope this deep dive into nonlinear Schrödinger equation and their engineering application was helpful. If you want to explore more about how mathematics fuels modern engineering, make sure to subscribe to our YouTube channel and hit the notification bell. For more in-depth tutorials, technical articles, and resources, don't forget to visit our website. We have a lot more exciting content coming your way. See you in the next video.